All right, let's get started. I always feel like I'm saying this, but I have like a new Zoom setup today for some reason. So hopefully everything will go okay. Y'all can see my screen and hear me, I assume. All right, well, welcome back after a break. How are things going? And do you have any questions about CS theory? It's all good. Got it all figured out.
I guess I could start. I was just wondering about 7.3. Maybe you could start with that.
7.3. This one is about max cuts and some eigenvalues and things. Okay. What are you thinking?
I guess in this one for part B, I was somewhat stuck on like how to show. So I guess for part A, I was able to get it using the Rayleigh quotient kind of formulation, but I wasn't
Okay.
sure how to like how to use that in part B. I wasn't sure exactly. Like I was trying to get like the Rayleigh quotient in a form where we can talk about like the the quadratic form of H or something, but I just like wasn't sure how to do that. So yeah, maybe we could just discuss that.
Sure. Why don't you tell me about how you did part A?
Okay. In part A, kind of we ended up using the the we reformulated the problem in terms of like the Rayleigh quotient, where we were talking about like the max. So it was like basically the reverse of like Cheeger's inequality almost. Where we used instead of using the min, we used the max there.
Let me like
Sorry.
write something so that we can all see. So
Yeah.
what should I write?
Um, I guess the thing that we were looking at was the max of I guess we were talking about like the inner product of F and LF,
All right.
and that like when F is the norm of F is 1.
Two norm of F is 1. Okay.
Yeah.
Okay. So yeah,
Yeah.
what can you tell me about this expression?
I think in this one, sorry. So in this one, we can kind of use like the same kind of thing with like Cheeger's inequality, where like basically that if you have like if you constrain F to be a characteristic function, so it's like 1s star,
Okay.
then it'll be worse than if you have worse than if you use the this form here, and this form is equal to the quadratic form in some sense of F, right? Because that
Okay, let me see. So well, this particular F doesn't have two norm 1.
right. I'm just saying that like we want to be able to say that opt of G
Okay.
is basically opt of G gives us a characteristic function like 1s or like indicator of S, but like we want to bound that by this Rayleigh quotient kind of thing,
Let's see.
essentially.
So like, okay, so let's see what's going on here. We have max cut. We're trying to partition it, fraction of
Yeah.
edges between us. Okay, so let's say you're saying like let S, which is a subset of V, achieve the optimum.
Yeah.
Cut.
Yeah.
Okay, so we could define, oh yeah, let's put a star just so we don't forget it's like generic. So we could
Right.
define like,
Right.
we could indeed like define, let's say F star to be like the indicator of this S star.
Yes, exactly. Right.
Okay, so now what?
So basically you can take the quadratic form of that f star there, and we
Okay.
claim, and that's like defined to be the, I'm not exactly sure, but it's like either 2 times the opt of g or like half. I didn't like, I wasn't sure about the constants there.
Well, it's not defined to be that.
Oh, sorry, it's not defined,
Well,
but
I
we
mean, like,
know that this would be like true, because this is just this
yeah,
is
what is
like
this?
what gives us the quadratic form, this quadratic form of f star, right?
Yeah.
And
Wait, so how
that
can we
would be,
relate this to the number of edges that
oh
cut
yeah,
by S star?
this is the number of cut edges over the number of edges, right?
Number of cut edges over,
Number of edges
is it?
divided by 2, I think, because it's the
Oh,
number
yeah.
of edges going out. Sorry.
Okay, so I was working on this with Josh, and basically that value right there is equal to the quadratic form, which is like 1/2 the expectation of um like f of x minus f of v squared.
Yeah,
Which
so let's see.
is-
So this is, yeah, indeed, this is always equal to this quadratic form. Put too many curls on the F well star there. Yeah, my pen is like a little bit different today, so it's like less nice. So this should be like this thing, right? This is the quadratic form. I guess we have to put star everywhere here.
Yeah.
B squared. Sorry for
Which
my
is-
poor handwriting. Yeah, which is sorry, what were you gonna say?
Oh yeah, which is then the number, it's the fraction of edges which step out from from V to not V.
Yeah, it's like UV that are going from like in S to this would be like not in S.
Oh yeah, S, sorry.
Star. So
Yeah.
whoa. Right. So how does this relate to the fraction of edges that are cut by S?
So the fraction of edges are the fraction of edges that go from S star to not S star, and from not S star to S star. It's twice that.
Yeah. So like fraction of edges, between S star and its complement. So this is like definitely true up to possibly up to a factor of 2.
2, right.
Let's just figure it out. Let's say like the whole graph is this graph. And let's say this is like S star. So the fraction of edges cut is 1. And what is this expression? You pick a random edge, you look at this difference. I guess if you pick a random edge, then like in this specific case, like FU minus FV will always be plus or
1.
minus 1, so it's square. So this whole expectation will be 1. So this will be giving you a half. So I think like this is probably a
2
half,
times. Oh yeah,
the fraction of like cut edges.
Right.
Okay. So I guess that means in this case, this quantity will be like a half times the opt.
Yeah, that's right. That makes
Okay.
sense.
All right.
Right. And then kind of following some of the intuition that that like Cheeger's inequality like has, in some sense, we can kind of like say that well, this will be no better than, sorry, this will be like this quadratic form will be upper bounded by like the max that f can take on, like the max, if you could, like, if you don't restrict f to be if you don't restrict f to be the specific indicator of S star indicator function, then like this will always be upper bounded by some like max f inner product with like LF. Does that make sense?
Yeah, this is at most this. That's true because F star has 2 norm at most 1. You might worry that it's like
Yes.
not so sharp though, because like f star, its 2 norm is like squared. Is like expected value over v of like f of v squared, which is like, this is like the volume, the fraction of vertices in S in this case. So it's like, potentially less than 1. In fact, it probably will be less than 1 in a typical case. You might worry a little bit that like, you're kind of losing a little bit here. You know what I mean?
I see. I see. So, because I mean, essentially, like that, like top form is essentially will give us the right-hand side of the equation, right? Because that's precisely what
Oh
we
yeah, this is
need.
indeed,
Yeah.
I mean, by basic linear algebra, this is literally lambda max or lambda,
Yeah.
n minus 1 of L.
Yeah, exactly.
Like
So
this
that's
is,
like kind of, sorry.
yeah. So we want, okay, so what are we trying to show? Trying to show that this lambda n minus 1, get my yellow pen here. Oh, you can't even see yellow. Let's try to do red. I'm having a hard time with my pen these days. This is supposed to be, okay, the optimum is supposed to be at most 2 times lambda n minus 1,
Right.
2 times its maximum eigenvalue. And yeah, let's see. So this is indeed maximum eigenvalue. Oh, okay, so it's fine. You're
Yeah.
saying the optimum is at most 2 times. Is that going the right way?
I think
Oh no, it's not going the right way.
I think it's the other way.
Yeah, well, we got
It's
the factor of 2 is like kind of
Yeah.
wrong. Like this observation we've seen so far is like, okay, this thing, when you choose f star to be like the indicator, a 0, 1 indicator of the optimum, that this quadratic form is a half times opt. And like definitely this is at most this, which equals the maximum eigenvalue. But this is giving us like, we put everything together here, that gives us like opt is at most 2 times this lambda of L.
Which is weaker.
Yeah, but we're trying to get, this should be like, it should go to like a half.
That's true. Maybe that was the mistake that made like B not solvable for me. So
yeah, this new pen system I'm having is so messy. Okay, I'll try to survive and stop talking about it. Yeah, okay, so we somehow need to improve this argument if we're gonna do like part A.
right. So essentially we need to
I mean, can't do anything. I mean, this is definitely true.
we basically need to involve like a factor of like a quarter or something in like in this to actually get the bound we want.
Yeah. Well, maybe we should just like examine what's going on and like this specific graph. It's a great graph.
Okay.
Let's just check what we know about this. So let's see. Okay, so the opt in this graph. So let's call this okay, G is this graph. Nice graph. So opt of G is 1. Because there's a cut S that cuts 100% of the edges. Yeah, and what do we know about lambda? The eigenvalues of L here. Let me just put max. Actually, do we know what this is here?
Would it be one as well because it's bipartite?
Pardon me?
I forget. I was just thinking like this is like bipartite technically,
right?
So it would be 2. So like I mean so it should be 1 like that. I mean I forget if it's 2 or 1. I forget whether like the lambdas or the kappas are like the scale versions. But yeah.
It's 2. Yeah, for bipartite
it's
graphs,
two.
the maximum eigenvalue is 2. And so in
Right,
this
so
case,
this
actually, I
should be
guess
two.
it sort of like exactly checks out in the sense that, in the sense that the second largest eigenvalue, or the largest eigenvalue here is 2, and then like times a half gives you 1, and that is indeed the op. So this is like an example where this inequality that we're trying to prove is exactly optimal, like tight.
Right.
Actually, let's try to remember, why is it 2? I mean, indeed,
'Cause-
it's true for all bipartite graphs, but
Right.
that means there should be, so, I mean, it means, okay, so what do we know? Like, this means that, there should exist like an f such that this quadratic form is equal to 2 times the 2 norm of f squared. This is like an f that maps the vertices into the reals. So yeah, for this graph, do you know the f that does that?
They're just 1, 0. Wait.
Let's see, 1 and 0. I think that works. So this thing is the quadratic form. Oops. Which is, as we saw, half the expectation over a random edge of fu minus fv squared. Okay, which is a half. Wait, is it a half?
Yeah, it should be.
Yeah. And then this one is the expected value of f squared. And what's that in this case?
That should be 1.
Pardon me?
Is it half? Wait. Half f squared. So f is like 1, 0. So it should be 1. Right?
I don't think so.
This is a volume of
Yeah, that's true. Since it is an indicator, it's like, it's a half. Yeah, I
it's a
mean,
half. Right. It's a
you know,
volume. Sorry, it's like
it's expectation over u drawn from pi. This is a regular
Right,
graph, so
right.
it's just uniform
Right.
distribution of f.
Right.
Let's just write it down. U squared. So like, okay, it's like half the time you get, this
1.
vertex here. You get, oops, yeah, 1 squared plus a half times 0 squared, which is a half.
Right. That's right.
Let's see. So, okay, so this turned out to be, whoops, this turned out to be a half.
Right.
And then this left-hand side also turned out to be a half. Oh, but it didn't quite work, right? Because like, half is not 2 times a half.
Yeah. So maybe we have to scale.
Yeah, so maybe we need a different function.
Right.
Does anybody have a suggestion?
Maybe we could have 1 and minus 1.
Yeah, I think that's
Yeah.
what we did in class. Let's try that as an experiment. So let's see. So, okay, if we did 1 and minus 1, let's just change this one to plus 1. Oops. This one minus 1. Okay, so let's work out this thing. It's expected value over a random vertex of f of u squared. Okay, with our new f, this is always plus or minus 1. So its square is always
Right.
1, so its expectation is 1. So like this bubble would be 1. Okay, what about this thing? The quadratic form thing. Okay, so it's a half expected value over a random, oops,
Half times 2.
edge fu minus fv squared. Okay, so I guess for any edge, there's only one edge. Like one of these will be +1 and one of these will be -1. You subtract them, you get plus or -2. And then you like square it and you get 4. So this thing in the brackets is always 4. So this expectation is 4. And then we times it by 1/2. And so therefore this is 2. Does that check out?
Makes sense.
Yeah, so I think for this one where it's like plus or -1, this is 2. And then it's good because like here's the factor of 2 and then it's 1. So at least here's okay, here's a case where everything is sort of exactly tight. So maybe suggest that like if this was G was your like entire graph, then it would be good to study this particular function. So perhaps that gives a suggestion of like maybe what to think about for part A.
Is there something where like volume of the cut set is at most 1/2, or the volume of like the set of the max for the max cut?
I mean, this is true in the sense that like if you have some G and you know S is some set of vertices. Okay, then in the maximum cut problem, like you count the fraction of all edges that are, you know, going between S and like negation, or not negation, but like complement of S. And this is like complement of S out here. And the volume of S plus the volume of like S complement is always 1. So one of these two numbers has to be at most 1/2. That's true. The smaller one is at most 1/2.
So could we consider functions instead of like just taking on values 1 and 0, taking on values of -1 and 1 then?
Yeah, you could do that. So
That's-
what do you mean in like
like
your
instead
suggestion in
of
the general case?
like something where instead of like the indicator of S, it's like the 2, what is it, like 2 times the indicator of S -1 or something, where it's like,
I see what you mean. Yeah.
yeah,
Okay, let's say if we have say S, we can even have S star. If we have in mind it's like the optimal cut is some subset of the vertices. I don't know, let's just like I don't know, let's just define, whoops. I don't know, G to be as you say, like the plus or -1 indicator. So +1 if U is, let's say, in S, and -1 if U is not in S.
right, because the example kind of indicated that would give us like kind of the bound we liked in some sense.
Yeah, at least for that one edge graph. So I mean, there's a couple, I mean, I guess there's a lot of quantities floating around like G, L, G, and like opt. And well, I guess these are a couple of things we have to consider. Well, there's also like, lambda n -1 L. So should we try like calculating one of these things and see what happens?
Sure.
What should we calculate?
Yeah. I guess if you do the quadratic form thing, then it's like very similar to the thing when we assumed the indicator of S, or like, because it's very close to the same thing. It's just like a transformation of that, and then you could just like use properties of the quadratic form to solve it or something.
Yeah, okay, well, let's calculate that. So this thing is this quadratic form, this expectation. pick a random edge, GU minus GV squared. Okay, so I can't make it scroll down anymore. That's weird. Okay, so yeah, what is this quantity equal to?
Okay. I was thinking that this would be, so I wasn't like sure about this specific one. Like, I don't know how to do this maybe, but like I was like, this is like the quadratic form of 2 times the indicator minus 1. So I can just use like
True.
properties of the quadratic form. And that'll
Okay,
make it a
yeah, we
little
can
bit
do that.
easier.
So this is indeed, as you said, 2 times the indicator of S star minus 1. This is sort of like a function, it's like a constant. Okay, yeah, we can do this.
Right.
Remember we like had this
Yeah.
local variance name for this. So we do have some properties. So for
Yeah, and
example, yeah, what is this equal to?
4 times the because 4 times the quadratic form of the indicator of S.
Yeah, very good, because we know that this this is like translating by a constant. That doesn't change it. And then this like multiplies it by the square of that constant. That's true.
Sure. Yeah.
Okay, so then this equals, we did this before. This was like 4 times, we
Half times.
Yeah,
yeah.
was it like half times opt?
Yeah, that's right. Yeah. So now it's like in the right form almost that we like need in some sense. If we can bound this by that Rayleigh thing, then we're good.
Yeah, so like this thing we just decided is 2 ops. And yeah, we're probably good. I mean,
yeah,
it's like this is always true.
Yeah, and that didn't matter. It didn't matter what F was there. So we
Well,
didn't
it matters a little, like F has to have
Oh,
this-
right. Yeah, that's true. Yeah, but like the eigenvalue, the max eigenvalue of L kind of, yeah. So I mean, but we I think we can still upper bound it by this now, right?
Perhaps. What
Or
is the
is
2
that-
norm of, what is this thing? 2 norm of G.
Should be less than 1. Wait, is that true? Wait, no.
Where's
Yeah.
G written down? Here's G.
Right. So I guess it's 2 times, sorry, it would be like 4 times the volume of S.
4 times the volume of S.
It's also the
Not so
square
sure.
of the expectation of x squared, which is always 1.
Oh yeah, that's right.
Like this, yeah.
Yeah.
Okay, let's assume, like, so we don't like right away. Let's assume you can finish 7A.
Yeah.
Okay. So what else? So 7.3b maybe?
Yeah, that's I guess, yeah. I'm not sure if like this like thing helps solve that, but like my intuition there was that essentially we can think of now L as like L plus diag H, but I wasn't sure how to then like take that diag H and like write it in terms of the F in the Rayleigh quotient thingy.
Okay. Perhaps let's pause here for a moment because we have spent some time on this question. So let's see. I mean, we can come back to it, and maybe we'll come right back to it. I don't know, but like, are there other questions that people have? Maybe about this problem, or maybe about a different problem?
I was looking at 1C. It was stuck. If we wanted to look at that one.
Sure, 1C. So here we're asked, okay, G is this hypercube graph. Okay, my favorite graph, pretty much. Right. So it looks like this. I can draw. Okay. For each set S, define this function phi S to be, oh, this expression, which maybe we even remember from the analysis of Boolean functions lecture. Show that each one is an eigenfunction for G's Laplacian L and determine all the eigenvalues of L. Okay, so let's see. What are your thoughts on this problem?
Yeah, so I haven't gotten to, I mean, it reminds me a lot of the analysis of Boolean function stuff, like you said, but I don't know. I don't know if there's not that much to work with this problem, but I can't get that far. Like for the first two parts, it helped to like think of the matrix vector multiply as a linear combination of the columns.
Okay.
And that helped a lot for the first two parts. And so I was trying to do that on this part, but yeah, so if you do that, you get that like L times phi sub S is like the sum of the parity function, or phi sub S of U times the youth column of L.
Well, let's just write all the definitions. So what is the definition of LF?
Of LF?
If F is any function from V into R.
Well, so I get, do we want it generally here or this specific L?
Yeah, generally.
Oh, it's like I minus K.
Yes, it's
Oh, sorry, I minus
K of F. Okay, that's true. So that's IF minus KF, which is F minus KF. Okay, so what's the definition of KF? Anyone else can, of course, pop up with an answer.
It's the transition matrix, or like it gives you the probability that you're, or it gives you the value of after like the next step, after like one step of a random walk.
Sort of. What is the, I mean, in the nature of like type checking, what kind of object is KF? What's its type?
So it's a function that maps.
Yes, very good.
Function. I'm trying to remember like the high level interpretation. There's just so many definitions flying around, but I think it's like,
there are a lot. Yeah, true. Yeah, so KF is a function, and what's
it like takes in a
value?
vertex and tells you stuff about the neighbors, right?
Yes. Does anybody want to say exactly?
Okay, yeah. I think it's was it just like the expected value of a neighbor?
Right? Yes. Well, it's the expected value when V is like a neighbor of U, F of V. So average, you know, like if you have F, it's like a labeling of the vertices by numbers, and then like KF, it's also a labeling of the vertices by numbers, and like the labeling for a specific vertex is like the average label around the neighbors. Okay, so that's nice. So let's do it for K phi S. How can we figure? Okay, so now we have to like think a little bit. What is K phi S out of vertex U? Well, I could ask, but I guess I could just be like a robot and write down like what we know. This is like the expected value over V, a neighbor of U, of phi S V. Let's do an example. So let's see, how can we do an example? Okay, so let's do let's do an example. Let's say like n is 3, or no, I think it was called d is 3. So like v is like all the binary strings of length 3. So let's say and I don't know, like let's say s is a subset of, let's say 1, 2. It's like a subset of 1, 2, 3. Okay, so phi s on a string u, if I recall, is just like u1, u2. So far, so good. So let's do an example. Let's say like u is, I don't know, plus, minus, minus. Then phi s of u is, I'm running plus and minus instead of +1 and -1. Well, it's this times this. So I guess it's -1. But what is k phi s at u? Maybe I'll let you answer this.
Should just flip it, right? Because all the neighbors have exactly 1 bit that differs. Or,
So you're saying it's +1?
oh, I guess I'm thinking about the general case now, but the, okay, wait, let me think for 1 more second.
Yeah. Who are the neighbors of u? I guess we can just write that down. The old neighbors. Let me ask, how many neighbors does u have?
Oh, oops, my, what I said would have been correct, but I forgot about the S constraint, so.
I see what you're saying. I think I know what you mean, yeah. Yeah, because I didn't take s to be everything, which is
Yeah,
really like the most illustrative case, but happen to not. So, okay, how many neighbors does u have?
it'll always have 3. Right?
Yeah, and what are the 3 neighbors in this case?
Minus, 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 plus, plus, minus, plus, minus, plus.
Yeah, plus, minus, plus, very good. And then what is phi s's value on these neighbors? So its value here is,
+1.
yep, plus here.
Wait, is S, sorry, I wasn't paying attention when you defined S. Is that the first and second numbers, or like what are we indexing by?
Oh yeah, I meant like this is 1, and
Okay.
this is 2, and this is 3, yeah.
Yeah, so then the next one will be plus, and then the one after that will be minus.
Right, okay. And if we average these up, we get,
I guess a third.
1/3.
yep, a third. So, okay, in this very specific case, this function value is a third. Yes, should we even draw like a picture? Somehow, like the graph looks like this. Phi s, I guess, I mean, probably is the product of, okay, maybe a picture is going to be like too laborious to draw. But I guess it'll probably look like something like this, like minus, plus, minus, plus, minus, plus, minus, plus. Probably. And like, I guess we maybe, we just did like this on some vertex whose label is minus, maybe this one. And you see, and we did like, we kind of averaged up its 3 neighboring values, minus, plus, and plus. Those indeed averaged up to 1/3. So like KU, or sorry, KF, probably like, okay, if this is US, sorry, keep running, this is phi S, when S is, 1, 2, and like K phi S, I think it'll be like probably we'll see. It'll be like minus 1/3, plus 1/3, minus one. Well, yeah, minus 1/3, plus 1/3. I'm just like, what I'm doing here is I'm looking at this thing and like averaging its 3 neighbors. It has one neighbor that's like minus, one neighbor that's minus, one neighbor that's plus. So the average value is minus 1/3. Okay, red on red is not my smartest move. Minus 1/3. This one will be plus 1/3. This one will be like plus 1/3. So you see what happened here? Like every time over here you had plus, like it got changed. Whoops, it got changed to like a minus 1/3. And everywhere here you had minus, it got changed to a plus 1/3. So actually, k phi s as a function is sort of the same as phi s up to a scalar multiple. Like the value at each corner like got multiplied by some value. Which value is that?
Negative 1/3.
Yeah, indeed. So what we kind of just saw here is that this is like literally negative 1/3 times phi s. And like that literally means that like negative 1/3 is an eigenvalue of k, whoops, k with eigenfunction or eigenvector, if you will, phi s.
Yeah, and it
So-
seems like that 1/3 value is like related to the size of S.
Exactly, indeed, it will be. Yeah. Maybe
Yeah,
I should do one more example, just for fun. So, for example, let me just try to quickly draw it. So let's say we do a different, I don't know, phi sub t. Say phi sub t, where like t has cardinality 1. So basically, this is, you look at the coordinates, which are +1, +1, -1, for example. And like phi t here is just like outputting one specific coordinate value, maybe the third one. So like phi t might look like the following, like it might be like, +1 on all the back faces and like -1 on all the front faces. Could look like that. And then again, if we like draw k t or k phi t. Okay, so what's the operation? Like the value here is like you average the 3 neighboring values, which are +1, -1, and -1. I guess the average of +1, -1, and -1 is -1/3. So like here you'll get like, whoops. Here you'll get like -1/3 at this vertex. This is like k phi t. And here we had -1. So I think long story short, in this case, again, like every value here will be like 1/3 the value it was back in the original picture. I think for this kind of phi t, I think like 1/3 is an eigenvalue. We'll get an eigenvalue of k with eigenvector this phi t, which, as you said, like for t is like cardinality 1. Does that make sense?
Yeah, that makes sense. I'm trying to think about what the general formula would be, but
Yeah, let's think about the general formula for like 2 minutes. Maybe we won't do all of it, but like, okay, let's try to think in general now. So let's say d is d and s is s. So like we're looking at phi s. So, okay, this labels the vertices of the hypercube with plus or minus 1s according to like the product of the coordinates associated to the set S. So K phi S at a point U is like average or expectation over a neighbor of U of phi S V. So like this will be like, it'll look like, V2 times V3 times V7 times V8 times V9 times dot dot dot, if like, for example, S is the set 2, 3, 7, 8, dot 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 dot. And if like U, like this specific U happens to be like, I don't know, plus, plus, minus, minus, plus, minus, plus, minus, 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 plus, minus, dot, 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 dot. We'll be looking at like V2 times V3 times V7, etc. Now, typical V will look like plus, plus, minus, minus, plus, and then like maybe in like one location, like this one, oops, it'll like be different. This is like a typical V. There's going to be D such V's, but like it's going to agree with you like on all the coordinates except for one. So yeah, what to think about this quantity? I guess it's like V2 times V3 times V.
So I guess we could like condition on whether the neighbor is, or I'm trying to split it up for the cases on whether the thing is flipped due to S.
Yeah. So like V, so yeah, this like phi S V, okay, it's like if, hypothetically it's V2 times V3 times V7, etc. So here's V2 in this box, this is V3. V7 is 1, 2, 4, 5, 6. V7, oh, I just missed the place where it was different. V8, V9. So let me ask you this. In this specific case where like S happened to be like 2, 3, 7, 8, 9, etc., and where like U and V had the property that they differed in like position 6, how would you describe what phi S of this specific V is?
It's just phi U, right?
Very good, exactly. So like, it seems like it's quite often, or like potentially the case, that like this equals phi SU, like sometimes at least. Sometimes.
Oh yeah.
Rather,
Okay.
maybe not sometimes, but like, I better say for some neighbors V.
Yeah, I guess we want a condition on like whether the bit that was flipped in going from U to V is in S, and then that's how you get the size of S thing involved.
Yeah, exactly. So like, you'll see, indeed, like if, V and U differ on coordinate I that's in S, then what goes inside the brackets?
Negation of.
Right,
phi.
you're getting like minus phi S U. Else, like if I is like not in S, you're kind of counting plus phi S U.
Yeah, nice.
So yeah, so the average, well, the average, I guess maybe see is like, the key is that it'll be like some multiple of phi S U. Indeed, as you say, maybe depending on the size of S. And that's good. Like that's the kind of thing we were seeing where like, K, where's my thing? Ka phi S's value at a string U was like some multiple of like phi SU. That's what you want for eigen vectors. Now, of course, we've been talking about K all along, and like, well, we originally got talking about L, but I guess, one can put the pieces together here.
Yeah, nice. That's good. That was helpful to think of K, I guess, rather than L.
Yeah, that's the thing. Like somehow, like K is like an operator or like a transformation that has like a nice meaning. Like L is just this thing that facilitates, its quadratic form being like the quadratic form that we care about. I mean, of course, they're not like, vastly different. It's like just this, but like, there's no inherent reason in life to like do this move except for the fact that, well, like LF is this nicely interpretable quadratic form. Okay, another question? We could also get back to, I suppose, 7.3b, but we could also do another question. All right, well, perhaps 7.3b, or any thoughts on this?
Yeah. So I guess like to start off with, I just thought he could potentially write out the whole thing, like in terms of instead of in terms of L, in terms of like L prime, and then expand in terms of L. So
Okay, what do you mean by that? What do you suggest writing?
on the right, first we can write out the maximum eigenvalue in terms of the Rayleigh quotient again, and just in this time, instead of using L, we use L prime first.
Okay, so what is this in terms of like, it's like the maximum of something?
Maximum of the inner product between F and L plus diag HF.
Yep, yeah. Okay, L prime. Yeah, so this is L prime.
Yeah.
F, and this maximum is over
condition, what? Yeah, the same F, it's F, constrained to be 1.
What's constrained to be 1? Yeah.
The F squared is constrained to be 1. Yeah.
Okay, yep, true.
So here my intuition was we had to do, so the L plus diag of H has no like interpretable form in terms of the graph stuff. So I was thinking if maybe there's a way of like rewriting this. Sorry?
No, doesn't it?
So I guess so I guess like this doesn't like give us like the nice kind of quadratic form of L. I guess maybe you could like use linearity of inner product, but I'm not sure if that like helps at all.
Maybe. Actually, it's a little bit similar to what we were just talking about. Like here we see L prime F. So what is the definition of L prime F?
Oh, it's L plus diag H and then I minus sorry. Yeah. Then we can think of L as I minus K.
Sure. Maybe I'll write capital H just so I don't have to keep writing diag H. It's a little alphabet soup here. Okay, so again, like what type of object is this?
A vector.
Yeah, a vector, a function, yeah.
Yeah.
And okay, so it's a function. So if I were to evaluate it at a vertex U, what would it give me?
F minus K F U plus each F U.
Yeah, F of U minus KF of U plus, okay, HF of U.
Right.
Okay, F of U we know. KFU we actually talked about. This is the expected value over V, a neighbor of U of F of V. Okay, and what's this?
It's another function
Mhm.
that just scales each. It's like a component-wise scaling of each of the nodes, or like each of the nodes by like hi or something. Or is it like,
Yeah,
can I think of?
H.
Yeah,
Well, yeah, indeed. That's a good question. What is literally, okay, so this is a number. What number is it?
I guess it's the f of u times h of u, where like hu, the index of like,
Yeah, very
yeah,
good. I don't know if we used function notation or like vector notation, but
yeah.
HU.
Basically they're equivalent, I would say here,
Yeah,
right?
they're equivalent,
Yeah.
yeah. So we could put, I suppose we could put it together. It's like 1 plus h of u, f of u minus this average. Yeah. Sorry, that should be a u here.
I see.
Okay. And let's see, we got to this because, well, then we were like inner producting this with f. So
Yeah.
we have this kind of long and mildly disgusting expression here. So what's this? I mean, how to write what this is?
I see. So we could say that this is I plus h, and so wait,
Well, let's first remember this. What does this mean?
oh yeah, it's the expectation of f times g.
Yeah.
Yeah, f to g. Yeah. I see. So we can expand that out.
Yeah, we could. We could indeed. So then this would become, well, expectation u drawn from pi. It's a little bit intense. F of u times, well, I suppose like this above expression.
I see.
It's like a little bit messy.
Yeah.
Although one thing to remember is like apparently, if you just do this, if you ignore the h, you know, we know
Yeah.
that this is FLF. We know this is like apparently like a nice quantity.
Yeah, that's a
Or like,
quadratic form.
yeah. So,
I see.
actually, you could imagine like subtracting these.
Yeah, yeah. I mean that's kind of like the linearity of like the inner product. You could like
Yeah.
have we could have said like the same thing where it's like inner product of FLF and then plus FHF in some sense.
Yeah, that's right. That's right. So like this thing, let's call it star, as you say,
Mhm.
equals FLF, which we know about, or like at least we have some thoughts about, plus inner product of FHF.
Right.
So what is this piece?
That is the that is going to give us the expectation of f squared h u. Sorry, f squared and h.
Yeah, FU squared, H of U.
Yeah. And
U
drawn
drawn
the
from
station.
pi. So let's see, what can you make, if anything, of this expression?
Is h of u independent of, like, there's some notion of independence? Like,
Maybe. I mean, H of U is okay. H of U is like some labeling of the graph. Like H is some labeling of the graph. If H is, you know, in white, I don't know. It could be something like this. I don't know if this is allowed. And then F is some other labeling of the graph. Maybe if F is in yellow. So this is like going over every vertex, I guess, according to its weight. You square F's label, you times it by H's label, and you average that up.
We want to use the condition that we know for H. Right?
Yeah, what is the condition we know for H?
I think it's just
Expectations.
At 0, the
oh,
expectation
so
of
can,
H is
can
0.
we use like Cauchy-Schwarz or
Yeah.
oh no, that's going the wrong way, I think.
Yeah, potentially. You're saying this, I believe this is the condition?
Yeah, that's right.
Okay, yeah. Yeah, you're right in the sense that, okay, these are good thoughts in the sense that, okay, here we are facing expectation of like the product of two things. And it's kind of a drag because, yeah, maybe you know some things about one and the other, but it's a bit of a mystery what to do when these things are multiplied together. Well, what are we trying to prove, by the way?
That this has the same that you can you can say op G is less than or equal to half times the top eigenvalue of L prime.
Yeah, and I guess we did show like this.
Right. So essentially, we want to show that the second term is 0 in some sense, or like
Perhaps,
at
yeah.
least
I mean,
not necessarily 0, but less than.
suggest you okay. I mean, I suggest you write down the proof of this.
Mm-hmm.
I guess you got to write it down anyway. Then reflect on how much that proof changes now that we have this like H business in there.
I see.
Well, maybe I'll leave it there. I guess we're kind of out of time. Any super quick questions before we wrap it up?